Okay, it's been a while since the last one. I've been chasing down a really stupid error. Before it really wasn't working, so I made a lot of small changes just to try and fix that error. Okay, first of all, what was the error? It's wait a minute, what was that? I think it's down here somewhere. Pulling to the yeah, the error was down here. You see result length times j. Well, before I was putting it like result length times I, which is completely wrong because result is because it's a two-dimensional array of filters. So it should be I equal x the x-axis, j equals the y-axis, and the result is always on the y-axis. So I was putting it as I here, and then also down here you have I and j. The j is supposed to match the result length here, but I was putting it as let me just show you what it does. Replace the I with the j here. It completely messed everything up. Would you like to rebuild? Yes. I thought it was working, but it turns out it wasn't working very well at all. See right here, it seems to be learning. It seems to be changing. The error seems to be going down, but eventually it messes up. It seems to be learning. It seems to be working, but it's really not. Yeah, now the error is going back up. It completely messed everything up. And I just didn't realize that. I thought it was learning, but it really wasn't. All because it's a single typo. Yeah, as you can see, the error is going for 37, 38, 0.38, 0.39. The errors just keep going up. Took me many hours to figure this out. So it changes from I here to J over here. And the lesson is just a single typo can really mess you up for hours and hours. Okay, let's change everything back. Result length times J. So that's pretty much it. Everything is working. Don't know what to say about it. Okay, a single error will mess everything. And now it should be working. The error is going down 1.0, 0.6, 0.4, 0.3, and 0.2, and it keeps going down. The error is going down and the image is clearing up. So now it's working perfectly. If you leave it running for a minute or so, it's going to go to double zeros. But it's not working too well. But it was the changes that I made. It's nothing really important, just cosmetic stuff. First of all, the transfer function. I put in a transfer function just to group all the transfer functions in the same place. So now when you call the transfer, you just give it which transfer you want and type neural network. When you create the transfer layer, you pass in a value and it's stored in layer value 1. That's the next change I made here. Network length or layer, not layer, or layer value 1. I just added an unsigned long. It's just a generic value that you can use for anything. The transfer layer just uses to save which transfer type that we're using. And in here, when I create the network, I just pass in add layer transfer and then I specify which transfer function I want. And that's pretty much it. Okay, so I built everything. So I changed the functions into a build network function because everything was getting too crowded down here. I need to move all this code right here into its own function just to get it out of the way. And you have run network, you have build network, which builds the network. You just create the network and add the layers. Right now I only have one convolutional layer. I can add more of them later, but it's running on CPU right now, so if I add more convolutional layers, it's just going to slow everything down to nothing. So I need to add GPU support later. Okay, draw network. It just what does it do? It just draws the output of the network. No, run network. Not draw network. Run network. It takes an image from the image list, copies it into the array, and then feeds forward, backpropagate, update weight. That's for learning. Oh, and also I have to change this function right here because having to copy the image into the neural layer into the null array every single time is just way too slow. Right now it doesn't matter because I'm not really doing anything. Well, so I just do it one by one, and then calculate the mean squared error, get output mean squared error, get output result, calculate the mean squared error by comparing with the source, and then print out the error. Okay, that's pretty much it. Okay, draw network. It goes to each layer in the network and then draw 20 weights, a maximum of 20 weights. If there's less than 20, then it doesn't do anything. Okay, so I will need to clean that up a lot later, but for now we're just testing everything. Make sure it all works. A lot of stuff really doesn't work here. Why do I have to? Oh, it doesn't really matter. That's not supposed to be here. Okay, right now we're just doing everything quick and dirty. We need to clean this up later. Okay, also cleaned up all the functions. Make sure all the function names match. In case you want to write code, all the function names are noticeable. Okay, now let's do some new stuff. There's something else I wanted to try. RMSProp. I've been reading up on this equation right here. See, trying to figure out how it works. Well, actually, I know how it works, but try to write code for getting it to work correctly. I think I got it, but let's see what we get. Okay, let's see if we can copy this right here. Okay, first of all, I need to copy momentum, just to make sure everything is right. Okay, what do we need? Momentum, update, RMSProp and AdaGrad are basically the same thing. There's a difference between them, but it's not enough to really be concerned with. So as a rule, I just call them the same thing. AdaGrad just sounds better than the RMSProp. Just know when I say AdaGrad, I really mean RMSProp, but like I said, I don't really care about the difference between them. Okay, what is it doing? Okay, the EG, I don't know what they call this. I've seen this equation before. EG is the adaptive momentum value. EG, adaptive momentum value. So it's like the vector, but it's not really the vector. Alpha, beta, sorry, gamma. Gamma. It's a gammas. It's a null array. Yeah? I don't care. Gammas dot gammas dot array data dot I. When I say gammas here, I just mean it just means a null array. I call it gammas because, well, it comes after alphas, and betas doesn't sound good. So beta is used for something else. Array data dot I, that's the previous one. It is basically the same as momentum. So vectors, we're just copying this right here. Okay, equals symbol means momentum. Yeah, momentum equals oh, actually it's right here. Just copy this right here. Momentum gammas, just replace gammas. Okay, it's not the same thing here. AG2. Yeah, just trying to figure out what it means here. Gammas times momentum times, no, it's not times. Yeah, it's the previous value. Momentum times the previous value. That's the same as for vectors, plus 1 minus momentum again. 1 minus momentum, exactly the same thing as here. Exactly the same thing. 1 minus momentum times the SC cost function relative to weight squared. Cost function relative to weight squared. So deltas. We have deltas here, so it's delta squared. Deltas times deltas. Okay, let's see if we can copy it here. Deltas squared. Okay, deltas times deltas. Okay, deltas times deltas. Okay. Okay, so that's pretty much here. We have to add an extra value. The extra value here, deltas and gammas. Gammas has to be stored along with vectors. So maybe we should just should we put it first or second? Yeah, we put it after, because it pretty much has to come first. Ah, stop doing that. Oh, come on. Ah, okay. Visual Studio is being stupid again. Gammas, deltas, deltas. Okay. What is that? Gammas. Okay, so that's the first step right here. Okay, for the second step. Whoa, what am I doing? For the second step, weight times weight minus 1 plus momentum divided by. Okay, I have to figure out what exactly this means. Ah, let's read it somewhere else because this is not making sense. Okay, I'm gonna read up on somewhere else because this one it's really different from the one I remember. I'm gonna read it somewhere else. Ah, this is making more sense. Okay, so vectors or weight vectors times momentum times vector plus 1 minus momentum that times delta squared, the derivative squared. Okay, why is it repeated here? Okay, so the weight update is weight times learning weight times the derivatives divided by the square root of the vectors of the of gammas plus epsilon. I remember what epsilon means. Epsilon is just a small value. Okay, so let's see if we can get an epsilon. Okay, good annual unit. Good annual unit. Let's see if I can figure this out. Not what am I doing? I'm getting ahead of myself here. Type null unit. Okay, epsilon. Okay, equals. It's just a small value, so 0.1234567 Yeah, 8 zeros. That should do. It's just a small value to prevent division by 0. Okay, but we still need the which part right here? We still need this part right here. NP square root. There, it's right here. NP square root plus epsilon. Yeah, 1 minus 8. Vector. VW beta, VW weight. Vector. Okay. Okay. Tab null unit. Gradient. Grad equals. Not grad. I need equal. Okay. Grad. Okay. Grad equals. Okay. This we're talking about this part right here. The square root of the vector. Not square root of the gamma plus epsilon. It's learning rate times the square root of the gamma plus epsilon. It's a little bit different from what I remember. Square root of gamma plus epsilon. What is it? It's learning rate times. I keep forgetting if it's the top one or the bottom one. Alphas times. Oh, alpha. What is alpha? Oh, alpha is the learning rate, or oh, I remember it's a different learning rate. Okay, let me read it somewhere else because this is not making sense anymore. Oh, the B here just means bias. That's just for the bias. That's why there's two of them. They don't label everything. Bias is weight. I didn't see that right here. Okay, alpha divided by alpha is the learning rate divided by square root. Oh, times. Oh, it's alphas divided by the square root of this times the deltas. Oh, that's making more sense. grad. Yeah, I got a grad. Okay, grad again. Grad is square root of the gammas plus 1 plus epsilon. Grad is the square root. Is it learning rate times? Yeah, it's learning rate divided by. Learning rate divided by. Okay. Learning rate divided by square root of square root of what? Square root of gammas dot I plus epsilon of gammas dot I plus epsilon. Okay, square root of I dot I plus epsilon. Okay, so now we have this is the gradient. Adaptive gradient, this is the gradient. Okay, which is divided by the learning rate. And now that's just our new learning rate. That's pretty much it. Grad. That just gives us an adaptive gradient. Okay. Okay, Kingsman. Okay. Grad equals array delta. So far, so good. So far, that's it. Okay, are we in the right place? Is it everything good? Adaptive. I just need to check if I got everything right here. Okay, let's read up on this. Where is it? Oh, where is it? Learning rate times epsilon. I lost it. Oh, there it is. Okay. That's pretty much it. So what is it doing right here? Okay, it's taking it's learning just like momentum. It's just adding an exponential decay thing. It's as you add new values, as you add new gradients, it multiplies those gradients by a momentum rate which is something like 0.9. So it just shrinks it and then adds a new one. So as you add new values, it's constantly shrinking, but it gets new values added to it. So as it goes larger, so right here, when you take the square root, it just it just gets bigger. So it slows everything down. The learning rate is shrinking or growing depending on how big the steps are. I'm not making a good explanation, but you can read up on that right here. RMSProp, AdaGrad, the same thing. As the step gets bigger and gets bigger or smaller, the learning rate changes to adapt to it. And that's pretty much it. That is AdaGrad. I don't know what else I can. Oh, one thing I need to add. This is kind of important. It's not really that important, but we need a second momentum value because I've been learning up and reading up on AdaGrad, and you know, for it to work, it can't just use the same momentum value as the regular momentum value. Got M2 right here. The regular momentum value is 0.9, but here we have to use 0.99 because I actually don't know why, but the momentum just have to be bigger. Okay, so use a different momentum value here. So let's change that M2. The other guy just use a different momentum value, and you get M1 right here. That's the momentum value for AdaGrad. Okay, gammas, vectors, gammas, deltas, everything's the same. Okay, now let's do the same thing again for Adam, the Adam optimizer. Okay, this one's slightly more complicated. Okay, a lot more complicated, but it's the same basic thing. We have the code right here. So, okay, so let's just copy it. Update Adam. So far, everything's been basically the same thing. The Adam optimizer. Okay, let's see if we can figure this out. What is it doing? What's the code right here? Adam optimization rule. Okay, the previous vector time equals this. The next vector, the next gammas. Actually, it's the same thing as I here. That this is the gammas, not the vectors. It uses gamma just like the old one. It's the previous gammas plus a learning weight divided by, well, so far it's the same. So far it's the same as the previous one. Let's just look at the code here. Gamma 1 minus gamma. That's the gamma here is into the learning weight. Gamma 1 times the delta. Is it the delta squared? Yeah, it's delta squared. Yeah, it's gammas 1 minus. It's the same thing. Momentum. It's it's momentum times. It's exactly the same thing as far as I can see. 1 minus momentum times gamma squared. So far, exactly the same, except there's one extra value. Well, so let's just copy everything. See how far we can get before things break. Okay, gammas times momentum plus 1 minus momentum 2 times delta derivative squared. Okay, is it right? Yeah, it doesn't say. Let me just read up on this and get back to it. Why does it do that? Fuck you! Okay, this is the best explanation I've been able to find. Okay, item optimizer. Okay, there's really no chance I can explain this. I'm just gonna try to copy this as best I can. Okay, there's empty VT. Yeah, there's this right here, whatever this means. Empty equals 1 minus 1 minus BT something. Yeah, the problem is I have to figure out what each one of those variables mean. Let me just read up on it and see what happens. Okay, gradient. Okay, 1 minus M2. So far so good. So far it's basically the same. 1 minus gamma times M2 plus 1 minus M2 plus derivative squared. There's a VT. No, VT. That's right here. Weight T. Yeah. It says VT, but I'm not sure which. VT is this right here. Okay. VT equals CUDA null unit VT MT. Just to put it in perspective. Okay. VT equals gammas dot RE dot data. Okay, I have to figure out what this one means. Data divided by, okay, divided by 1 minus VT, VT hat. It's not just VT, it's VT hat. VT 1 minus divided by BT2. What is BT? Okay, let me try to figure out what BT is. Okay, BT is 1 minus momentum. Yeah, 1 minus M2. Why is it 1 minus M2? Yeah, it's really getting hard to figure out. 1 minus M2. Okay, we got BT. Okay, gammas. Now we have vectors. Okay. We're supposed to divide by our performance. Adaptive gradients. Since MT and VT are both each as 0 based on the above methods, it's observed that they gain in tendency to be biased towards 0. Oh, that's what it's for. The optimizer fixes this by computing bias corrected MT and VT. That's what it means. It's a bias corrected thing because it starts at 0, so we have to update it to something that's not 0 to control it. That's what MT and VT mean. Okay, why is it used? Yeah, weight update equals MT hat plus VT plus epsilon, square root of VT plus epsilon. Okay, that made no sense, but let's try and see if we can get it to work anyway. Vectors. Okay, we have to correct the empty according to the vector thing. Vectors.I plus, now it's divided by 1 minus momentum. Oh, momentum 1 and momentum 2. 1 minus momentum. Oh. So this right here is a correction. Because it doesn't work the way it's, because it started at 0. That's what it says right here. I'm gonna have to read up on this just to figure out what any of this means. Okay, 1 minus momentum. Okay, now we get to grad. Okay, grad equal learning rate times the square root of gammas. That's why you have to do it that way. Because we have to correct it, because if we use gammas directly, it does something wrong. Okay, gammas plus epsilon, vt plus epsilon. Okay, so here, so weight update has to be mt. Weights plus mt times grad. Okay, this is somewhat different. Oh, so we can't multiply. Oh, this is what I've been struggling with here. So you can't multiply the derivative directly by mt, by the gradient. So you have to correct the gradient, mt plus weights times mt times gradients. Mt times the new gradient. Wow, this is complex. This is complicated here. So I've been asking if we should gradient times deltas up here instead of gradient times vectors. But in here it says to multiply directly by the gradient. Wow. Yeah, these numbers right here, it's really confusing. What means what here? I'm just trying to figure out what means what. Okay, so let's see if we got this right. Gammas equals 1 minus m2. Vt equals 1 minus 1 divided by is equals gammas divided by 1 minus m2, and vectors equals previous vectors times momentum plus 1 minus momentum times the deltas, the derivatives. Empty is a vector is a correction for whatever the vector was before. You take the vector and apply a correction just to make sure that it doesn't mess up for whatever reason. And gradient is learning rate divided by square root of vt, the square root of vt plus epsilon to prevent it from divided by 0. Is it square root of vt plus epsilon? I always struggle. Do you put the epsilon inside or outside? It's tiny, so outside doesn't even make any difference. Okay. Okay, at vt square root of vt times epsilon. Just to be absolutely clear, just okay, is it right? Yeah, it's right. Just put epsilon outside. Doesn't really make any difference. It's just to prevent division by 0. So putting it out here, whoa, what am I doing? Okay, grad. Okay, just to make sure it works. Square root vt plus epsilon. I'm just trying to interpret this as best I can. A lot of it's not even clear. So I'm pretty sure it works. So let me just test it, make sure it works correctly. Okay, let's move it in and see what it gives. Okay, where is it? Okay, update weights, convolution update weights. Oh, this is problematic. Update momentum. I need a way to select which one I'm using because having to change everything each time just doesn't really make sense. Okay, do we have it? Neural array. Let's try AdaGrad first, see if it gives anything. Okay, I also need a way to test to make sure that to compare things. AdaGrad and bias. Where's bias? Neural layer bias. Okay, like I said, I need a way to select which one I'm going to be using. Oh, we need gammas. We need gammas. Okay, type neural layer. There's something we need. Alphas, gammas. We have deltas already, unlike betas, so let's just call it gammas. There's the gammas. Okay, so convolution has to create gammas, alphas, gammas. Okay. Okay, unlike alphas, gammas have to be set to 0. Because otherwise you get really weird values. Okay, and for bias, where's bias? Yeah, bias is over here. Create vectors gammas and set it initialize to 0. Okay, we have to set it to 0 and update AdaGrad, and we add it up here. And of course, okay, gammas. Okay, update weight gammas. Delta's learning weight. So convolution should be basically the same. Update AdaGrad gammas. Gammas, deltas. Okay. Wait a minute. Is it? Oh, where are we? Yeah, gammas comes first, then vectors, then everything else. Okay. So it should be okay. Build, rebuild. Okay, so it works. So, actually, it builds. So I'm not sure if it works actually. Okay, is it working? 0.5, 0.5. No, it's not working. Okay. I don't think it is working. Yeah, I don't think it is working. Something's wrong. Something's very wrong. Let me just go check to see what I missed. Yeah, I just figured out what the error is. Oh, that was stupid. It's supposed to use the alphas right here. I was copying, wait a minute, where am I going? I was copying from the bias layer. And for the bias layers, the deltas is the same thing. The deltas and the alphas, you don't need to calculate momentum. That works perfectly fine. Because the gammas and the vectors and the deltas are all the same size. It's a really stupid error. Everything's the same size, but for the convolutional layer, the weights and the outputs are definitely not the same size. Not at all, not even close. So when I say deltas right here, what it really means is alphas. Okay, so I just tested momentum to put in AdaGrad right here. And now let's see if everything works. That was a really stupid mistake. Is it working? Yep, it's going down. It's learning. It's learning, it's learning, it's learning. Yep. Okay, so that's not AdaGrad, that's anything. Okay, I have no way to test if it's learning faster, but just to make sure that it works at all. Okay, it seems to be learning, but not very quickly. But it starts at a random location, so that will explain it. But the learning, the error is going down, it's going down, it's going down, and it works. Error is going down below 0.01, and error is going down. Well, I can't tell if it's working faster because we don't have enough images to make sure of that, but all that matters is that it works good enough. Okay, update AdaGrad. I really have to fix this. Update Adam. Adam and AdaGrad works better. So we're gonna have to add something to select between them, because I don't want to have to retype the code every single time. Okay, AdaGrad seems to be working also, I think. 0.12, 0.7, 0.5. Yeah. Well, it didn't fail. Well, that's not good praise, but it didn't fail completely. 0.2. Is it even working faster? No, it's not. 0.21, 0.19. Okay, so it is working. Later, I'm going to have to figure out a way to test how well everything is working, instead of just saying it's working versus not working. Square root VT epsilon, grad, learning rate, MT grad, 1 minus momentum. So everything seems to be working. So